So, Stelios said the title of my presentation, which is a joint effort with a lot of other colleagues. What we needed to solve. Everything in the ocean in the future is going to be digital, it is going to be autonomous or semi-autonomous. The sea is a rather not very friendly environment, as we all know, and this raises also the cost of going there. We cannot be every day underwater, and of course, every time that we go, we have elements like the weather that influence the time that we can spend in an effective and efficient way. So, in order to answer a call from the European Union, that it was challenging us, saying that the climate change is bringing a lot more power to the elements of the sea, and also in the underwater cultural heritage, and the cultural heritage in general, and also that anthropogenic pollution might hurt the cultural heritage both on Earth and underwater. We developed a system which is currently at TRL 3 level, and we want to raise it to TRL Technology Readiness Level 6, of autonomous, continuous monitoring of a lot of different elements and substances in an underwater environment relevant to the underwater cultural heritage artifacts and sites. This is the idea, and to do it in a much more effective, efficient, safer, and economic wiser manner. Also, this is in line with the Ocean Decades outcomes that the UNESCO wants to achieve, because at the end, the underwater cultural heritage is in the ocean, and the things that are doing as far as technologies are relevant also to other fields than the underwater cultural heritage. So we want to develop things that are going to support the sustainability management of the ocean, and we are going to make a safer oceans due to different hazards. Now, as we said, in the NERITES project, we are focusing on conducting a systematic, autonomous, remote survey and monitoring underwater cultural heritage, monuments and artifacts using advanced, non-destructive technologies. And of course, we do this in a lot of different manners. First of all, we have a group of industrial partners, and saying industrial partners, I see the colleagues in archaeology, we mean the archaeologists, because these are the partners that are putting the needs, the requirements, and are the partners that are going to test the technologies on site, and the partners that are going to evaluate the results. And of course, we have the technology partners that they are developing the technological platforms. Our key objectives is to have autonomous system of monitoring the underwater cultural heritage, to be able to have a preservation assessment of the condition, to have alerting mechanisms if something goes wrong, to have a cost-effective solution, this is very important, and of course to have a greener solution. We want to avoid plastic, for example. Of course, it's not possible to avoid plastic, as we see a lot of underwater autonomous vehicles still using plastic, etc. But we are trying to do everything to be in the greener approach. So, how we are going to do this? We develop an autonomous platform consisting of AUVs. We are going to combine 2 AUVs together in order to have more lifting power. We are going to use a docking station in order to charge to develop it on site, to be able to charge the AUV at the bottom, and also with renewable sources on top, and also communications devices on top. We are going to use sensor technologies of LIBS and QCLs. These are laser type technologies I'm going to explain to you, in order to assess elements on the archaeological artifacts and on the environment, the column of the sea. We are going to use advanced image processing, so photogrammetry and 4D to be able to know how the biological, let's say, factors are influencing the whatever problem in the underwater cultural heritage. So the LEAP sensors are sensors that they are sending 2 laser beams in very quick manner, and they can hit without destroying whatever we want to hit underwater, like an amphora, a metal, stone, or whatever other type of element. And we can, in this way, we can know the substance that exists on this artifact. What is the problem still that we haven't solved? We do not know the quantity. So how you can measure the impact if you don't know the quantity of phosphorus or other elements that you find there? And this is not only the problem of the LEAPS technology, this is also the problem of the QCL technology, which is again a laser for the column of water. It can say here that we have some substance of this and that, but we do not know the quantity of this and the quantity of the water. And this is a serious problem. Marco knows it, it's something that we are facing, but still it's a research project and TRL 3 level, so we have to solve it. The laser, it's going to be able to move in 90 degrees in order to be able to hit, let's say, in a distance of 10-20 centimeters, whatever object. Sorry. Okay. Here you can see this was an initial drone. Now we're going to use only the 2 of the 4 AUVs. And we're going to have in the middle the LEAD and the QCL and the cameras, etc. So to see a little bit of how the structure is standing. The quantum cascade laser, as I told you, is working to analyze the elements in the column of water to see mainly any pollution. The photogrammetry is something that already speakers have talking with. What we are going to do, and Stelios here knows it better, we are going to try to create patterns of how the biological factors on a monument, underwater monument, affect its stability, its rotation, or its condition in general. And to want to be able to see this and study it in time, and to make also forecast. So if we see a situation like this and we know that the biological factors are going to develop, which is the most critical parts that we are going to have problems in the future. Here you see a picture of one of the 2 pillars of the AUV platform, the one of the 2 AUVs. And this is a type we haven't developed yet exactly of the buoy that we are going to use for communication and powering the system, the docking station at the bottom of the sea. The operational level working is going to be at least 100 meters of the AUV and the platform at the docking station, and we are going to use them, let's say, at the bottom up to 55 meters at the pilot sites. Of course, we are going to develop also the control center, because when we have an AUV, which is also a tether AUV at the beginning, and then you take out the cable in order to leave it alone, you must have a control panel in order to be able to give the mission plan and what the AUV should do underwater. So this is again one of the objectives of our work. And of course, we have the different sensor technologies. We use also other sensors embedded on ROVs because we want to have, let's say, a test of the measures that we are taking to be able to make certain that everything is working properly. And another piece of our work is to develop protocols, because what we are talking about is going to an underwater archaeological sites with a lot of different equipment and trying to do a number of measurements. Yes, but how we are going to do this step by step in a very detailed way, how we are going to make certain that it's an effective and efficient way, and a safe way also for the underwater cultural heritage sites. So we develop a lot of protocols and a lot of procedures of how all of these are going to work, and this is a work in combination of the technology partners and the archaeological bodies. The pilot sites that we are going to use them, one is at Furni Islands. I think all of you know Furni Islands is in the east part of the Aegean Sea, near Minor Asia. It's a complex of 20 small islands, and the survey there, led by Professor Zos Bouchouflakis, has already discovered 58 wrecks, and the site that we're going to use is Aspros Kavos, which is a very difficult environment, up to 55 meters depth, and this is a challenging also environment for the technological partners. The other site is a different site, much more near an urban area. Salo site is the Pozzuoli Baia in Italy. It's a submerged site. It used to be the area of the villas of the Roman high class in the Roman area. And you can see a typical picture of this site. And these are, we have other conditions, not very clear water, depth around 3 meters, maybe a lot of pollution due to the urban environment, which does not mean that maybe we do not have pollution also in Furni, but that's why we have to measure everything. And we have developed the notion of decay scenarios. So we have small case scenarios when we give, let's say, a plan to make a single measurement of a single artifact. So the AUV will go, do just one task in one position and come back. The large-scale scenarios, in these large-scale scenarios, the AUV will go do several measurements with different technologies, maybe even in different, let's say, sites, and also maybe in more than 1 day. And we have also the use case scenarios, and we have developed very, very detailed protocols in how everything is going to operate step by step. So to analyze all the problems before we're going to go on the sea, because when we go on the sea, we have a high cost, the time is very limited, and the pressure is high to deliver results. Here, I mean, you cannot see a lot of things, but I can say to you that we are going to measure a lot of different things at the sediment and the water column and the artifacts, and we're trying to see what kind of metals or what kind of other substance exists there, but still we cannot measure quantities, as I have already told you. So if we are going to use to see the titles of 4 use case scenarios in Villa of the Pisoni in Baia, we're going to monitor the physical and biological degradation of mosaic and wall structures. And of course, we are going to do this with preliminary optical 3D mapping of the villa, preliminary cleaning of selected areas in the wall structure and mosaics, assess the biological degradation of wall structure and mosaics using automatic image analysis, and assess the physical degradation of wall structure using 4D analysis on 3D models. Just to say that we can also clean an area using the laser. We can hit, let's say, the epiparos, the whatever we have there, until we are going to reach on the artifact. Another example of Villa Pisoni is to monitor the anthropogenic impact on the site, because it's close to an urban area. So assess the concentration of phosphate and nitrate in the water column using the QCL measurements, assess the concentration of volatile organic compounds in the water column using again the QCL, and of course using the LIPS assess the presence of heavy metals in the sediment, wall structure and mosaic. In Furni, it's a little bit different. We are going to monitor the physical and biological degradation of wrecks, and when we say wrecks, of course, mainly we are talking about the cargo, the amphoras, preliminary cleaning of selected amphoras if necessary, measurement, assess of the biological degradation of amphoras using automatic image analysis, and measure assess the physical degradation of the wreck using 4D analysis on the 3D models. And finally, we are going to monitor the anthropogenic again impact on the site, measure the concentration of volatile organic compounds in the water column, again measure with the lips the presence of heavy metal on sediments, ceramics or metal objects, and of course measure the exposed areas without coronation on metal objects, mainly iron or lead using the lips. Concerning the evaluation approach, we are going to use different kind of evaluations concerning sensor measurements, of course, mission logs, user surveys, and expert observation. We have three types of, let's say, qualitative measurements. The desired performance achieved, so can we reach 55 meters and work without losing the HUV, for example? Very typical things. Quantitative target reach, so to reach this depth or to reach this measurement. And of course, the quantified qualitative evaluation results, so in a scale of 1 to 7, how well we perform, how effective we were, how efficient we were in different measures. And we have developed 15 key results, let's say, that we want to achieve, and another 35 key performance indicators. So we have developed a very thorough evaluation methodology of how we are going to evaluate the results of the research work. Concerning the shareholder engagements, here I just want to mention that, okay, this is technologies developed for underwater archaeological sites and practitioners like underwater archaeologists, but this work and this technology is relevant also, if you see the last paragraph, to other professionals working in the underwater environment. So we have this dual use, not in the sense of defense, of course, but in the sense of going to other also fields, so multiple use of the same technology in different fields. Just something about the project. The project is called NERITES. We're a number of partners throughout Europe. You can see here the countries participating. Here we have a list of the partners in this project. We were 13 partners, and most of them are technological partners. We have a lot of technological developments composing the challenge that we have to face. The project is more or less of 4 million euros, and it's going to end by December 26. So it's a 3 years project. We are running it for 1 year. And if you want to get involved, you can find us in several social media or web sources. Thank you very much.
Very much.